In this video, we're going to determine the dimensions of a cylindrical can of given volume that minimize the overall surface area. We have a cylindrical shaped aluminum can with a capacity of 500 centimeters cubed. We want the dimensions that create that can but use the least aluminum possible. This is good for business, it keeps costs down, and it's good for the environment. So let's minimize that surface area. To do that, we first need a formula for what the surface area is. Well, there's a circular surface at the top and a circular surface at the bottom. So the area of each of those is pi r squared. So that total area there will be 2 pi r squared. But there's also this area along the side. Now let's think about that for a moment. What we've really got there is a rectangle. And it's wrapped around a circle. So the circumference of that circle is the length across the top of that rectangle. And then the width here is really just the height of the can. Well, what's the circumference of a circle? It's 2 pi r h. It's 2 pi r. And the width of that rectangle is h. So the surface area of the sides is just 2 pi r h. So the total area is given at the bottom as 2 pi r squared plus 2 pi r h. Now we have two variables there, r and h. So what we would like to do is isolate one of them. We see a pattern arising here that we often want to get each variable in terms of r when one of the variables in our optimization question is r. So that's a pattern that happens, a fair bit. We'll keep that in mind. So we know that volume of a can is pi r squared h. So that means 500 is pi r squared h. Well, what we can do is divide both sides by pi r squared, and we'll get an expression for h. So the surface area as a function of r is really 2 pi r squared plus 2 pi r times 500 over pi r squared. And multiplying, we get 1,000 pi r over pi r squared as that second fraction. We can simplify that a bit by dividing numerator and denominator by each of pi and r. That gets us to 1,000 over r, which is the same as 1,000 r to the negative 1. So our surface area formula on this previous slide is shown at the bottom, and we can determine that derivative pretty simply using the power rule. 4 pi r minus 1,000 r to the exponent negative 2. Now, we're not going to do a domain analysis in this question, and we're simply going to let that derivative equal to 0. So we can multiply each term by r squared, and when we do that, we get 0 equal to 4 pi r cubed minus 1,000. Well, if 0 equals 4 pi r cubed minus 1,000, then that's like saying 1,000 is 4 pi r cubed. Or in other words, 1,000 over 4 pi is r cubed. Dividing numerator and denominator each by 4, we get r cubed is 250 over pi, which means r is the cubed root of 250 over pi. Now, sometimes a question like this indicates you can use decimal approximations and round the result. However, let's avoid doing that because it's more fun not to use those approximations, and also because there's a pretty cool result at the end of the solution. We know from earlier on in this presentation that h is equal to 500 over pi r squared. Let's re-express that as 500 times pi to the negative 1 times r to the negative 2. What ends up happening then is we can say 500 pi r squared is equal to 500 pi to the negative 1 r to the negative 2, as we just said on the previous slide. But earlier we had said r is equal to 250 over pi to the exponent 1/3. So saying r to the negative 2 and subbing in our value for r, we get the expression shown here. Now, we can multiply these two exponents and get 250 over pi to the exponent negative 2/3. And then in the next line, we're going to invert this base, thereby allowing us to make this exponent positive. And we're going to break up that 500 into 2 times 250. So what we really have now, if you look at that bottom line, we've got 2 times 250 to the exponent 1 times pi to the exponent negative 1. And then we're going to break apart this pi over 250 to the 2/3 and call it pi to the 2/3 times 250 to the negative 2/3 because 250 is in that denominator. Now, if you look at that bottom line, we've got one of those factors is 250 to the 1, and another one is 250 to the exponent negative 2/3. Well, if I'm going to multiply those two, I just have to add the exponents. I just have to evaluate 1 minus 2/3. Well, 1 minus 2/3 is the same as 3/3 minus 2/3, which is 1/3. So I can re-express the exponent on 250 as being 1/3. So I'll call this 2 to the 1, 250 to the 1/3. And now I need to look at these factors of pi. I've got a pi to the negative 1, and I've got a pi to the exponent 2/3. I can evaluate that by simply adding those exponents. A negative 1 plus 2/3 is the same as negative 3/3 plus 2/3, which is negative 1/3. So I've got a pi to the exponent negative 1/3. So once again, the 2 to the 1 stays. The 250 to the 1 times 250 to the negative 2/3 has become 250 to the exponent 1/3. And the pi to the negative 1 times pi to the 2/3 has become pi to the negative 1/3. And this is what we get in our next line. Well, we know that we can make a new fraction where 250 to the 1/3 is in the numerator, and we can put pi to the positive 1/3 in the denominator. So we've got 2 times 250 to the 1/3 over pi to the 1/3. Well, this is the same as saying 2 times 250 over pi to the exponent 1/3. Now, that's like saying 2 times the cubed root of 250 over pi. So we've now got a value for h. So the dimensions creating the can that uses the least aluminum will have a radius of the cubed root of 250 over pi in centimeters, and a height of 2 times the cubed root of 250 over pi, again in centimeters. And notice what that means. The minimum area is occurring when the height is exactly equal to double the radius. Isn't that cool?